Hey everyone, and welcome to this explainer. Today, we're literally looking behind the curtain of modern artificial intelligence. We so often experience AI as this magical conversational entity that just knows everything, but finding out how it actually works under the hood is a fascinating journey into some really advanced data engineering. We're going to explore the true system design of modern AI infrastructure, a framework called Retrieval-Augmented Generation, or RAG for short.
So let's just start with a super fundamental question. When you ask ChatGPT a question, where does the knowledge actually come from? It's kind of a great mystery, right? Well, a standard large language model, or LLM, is essentially a massive probabilistic reasoning engine. It doesn't actually know things like a database does. Instead, it relies on patterns it memorized during its training phase. And the catch? That training data is entirely frozen in time. So how on earth do we get an AI to answer questions about a highly private company document, or even just yesterday's news?
The answer is a massive architectural shift. You see, a simple chatbot relies solely on its frozen memory, basically just guessing the next most likely word. But a professional enterprise-grade AI, that is a multi-stage pipeline. By connecting the language model to an external dynamic database, we transform the AI from a closed box into an active, intelligent researcher. This entire pipeline is what we call RAG, and the whole thing begins with how we actually prepare the data.
Okay, let's dive into stage one, data indexing. This is all about building the offline pipeline.
Before a user even types a single word into a chat box, there is this totally unseen digital world where raw data begins its transformation. Think of it like a giant assembly line for knowledge. We start with data ingestion. Picture a massive river of raw PDFs, markdown files, and enterprise websites just flowing into the system. But here's the thing, the AI simply cannot read all of this at once. It's too much. So the pipeline runs the data through 4 absolutely crucial steps to prepare it. Let's break down exactly what happens to a document as it travels down this line.
First up, we actually have to chop the data up. In the industry, this is called chunking. And why do we do this? Well, because large documents are incredibly noisy, and every single language model has a finite context window. That's basically a strict limit on how much text it can process at any one given time. So by breaking a massive, say 100-page manual into smaller, coherent semantic pieces, we create manageable, bite-sized units of knowledge that the system can actually digest.
Now, this next step, this is where the engineering honestly feels a little bit like magic. It's called embeddings. See, a computer doesn't actually understand English. It understands math. So we pass these text chunks through a specialized model that converts human meaning into high-dimensional numerical coordinates. Imagine this vast, glowing, multidimensional space where concepts with similar meanings are physically grouped together, so the words dog and puppy will literally have coordinates right next to each other. We are transforming raw text into pure mathematical meaning.
Finally, all these numerical coordinates, they need a permanent home. Enter the vector database. Now, these are definitely not your traditional row and column spreadsheets. These are futuristic, highly advanced storage systems designed specifically to organize data by semantic similarity. They store our embeddings permanently, which allows the system to perform massive, rapid mathematical matching later on. And with that, our offline pipeline is officially complete. The knowledge is mapped, structured, and just waiting to be used.
All right, moving right along to stage 2, semantic retrieval. This is where we enter the online pipeline.
Now, this is where the system comes alive in literal milliseconds. During what we call naive RAG, the online pipeline activates the exact moment a user asks a question. The system instantly runs that exact same embedding process we just talked about, but this time on your prompt. It turns your query into a numerical vector, drops it straight into that glowing vector database, and runs a lightning-fast similarity search to find the chunks of data that are closest in meaning to your question.
The absolutely crucial takeaway here is that we are talking about semantic search, not keyword search. Think about it. If you search an old-school database for machinery fixes, it only looks for those exact rigid words. But semantic search? It captures the actual intent. It knows that machinery fixes mathematically aligns with equipment repairs. So it uses nearest neighbor matching to pull the top most relevant chunks, known in the industry as top K retrieval, even if the vocabulary doesn't perfectly match up. It is incredibly smart.
Which brings us to stage 3, grounded generation. It's time to synthesize the evidence.
Okay, so we've got the user's question and we have mathematically retrieved the absolute best possible evidence. Now we synthesize. This step is called context assembly.
We don't just blindly ask the LLM the user's question. Instead, we dynamically construct a massive, highly specific prompt. We literally inject those retrieved chunks of text right alongside the original question, with very strict instructions. Answer the user's question using only the provided context. We are essentially augmenting the prompt to ground the generation in reality.
There's this quote from the source material that really stood out to me because it highlights just a massive paradigm shift in AI. The model is no longer answering from memory alone. It is answering from retrieved evidence. It's kind of like taking an amateur home cook, handing them a Michelin star recipe book, and telling them to follow the instructions exactly. We are relying on the AI for its reasoning and its language skills, absolutely not its factual memory.
And the benefits of this grounding process? They are totally transformative for sure. It drastically minimizes AI hallucinations. You know, the model's really annoying tendency to just confidently make things up? Plus, it integrates up-to-date dynamic information instantly. And because we know exactly which chunks of text we fed into the prompt, the AI can actually provide transparent citations. Crucially for businesses, it protects enterprise data privacy. Your sensitive data stays locked in your secure vector database. It's never baked into the public model itself.
Now let's take a quick look at advanced RAG system engineering, moving beyond naive retrieval.
Okay, so what we've described so far is incredibly powerful. But honestly, professional RAG systems aren't just a simple straight line from question to answer. They actually use iterative, recursive, and adaptive flow structures. The system might loop back on itself. It might realize, hey, the initial search wasn't good enough. Actively rewrite the user's query to be more precise, and then search again. It routes intelligently, dynamically figuring out if it needs more external knowledge before it even attempts to speak.
These optimization layers, well, that's where the real heavy-duty engineering happens. We have pre-retrieval query rewriting to clarify what the user actually meant. We use super advanced index structures like raptor trees, which recursively summarize long documents into a hierarchical tree. And we implement post-retrieval re-ranking. This is a really crucial step that acts kind of like a strict bouncer at a club, scoring and filtering the retrieved chunks so that absolutely only the highest quality data makes it to the final generation model.
This leads us to our final concept, a living knowledge infrastructure, which is the paradigm of modular RAG.
As we look back at this entire journey, from raw data all the way to intelligent output, we arrive at the core takeaway of this whole explainer. A modern RAG system is not just an AI model. It is a living knowledge infrastructure. It is this absolutely brilliant fusion of raw data engineering, advanced vector mathematics, rapid information retrieval, and the conversational power of large language models. It literally transforms static documents into a dynamic, interactive brain.
So I'm going to leave you with this final thought to kind of spark your curiosity going forward. The AI models themselves, they will always get smarter. That's a given. But the true differentiator is the data you connect them to. As this technology continues to evolve, how will your organization's data shape its intelligence? The tools are already here, the architecture is built, now it's really all about what you choose to build with it. Thanks so much for joining me on this explainer, and keep exploring.